Okay, today we're going to talk about momentum and impulse. Momentum is one of those words that we've used in our everyday life, I'm sure. And when you think of an object that has lots of momentum, what are you thinking about? You're probably thinking about something that's really big or really fast or both. So we know that an object with a lot of momentum will have a lot of mass and or a lot of velocity. And an object like that is really tough to stop. So we're going to define momentum. And we're going to use the letter P to stand for momentum, and it is a vector. And we're going to define momentum as mass times velocity. Now, let's check out our units here. Our units for mass are going to be kilograms. Our units for velocity are going to be meters per second. So our unit for momentum is simply going to be kilogram meters per second. We don't have a special name for this. We're just going to leave it as kilogram meters per second. Now, let's take a look at a simple object, and let's say that it's a 3 kilogram object, and it has a velocity to the right of 4 meters per second. The momentum then, because it's a vector, is going to be 3 kilograms times 4 meters per second. So we're going to end up with 12 kilogram meters per second. We'll go with to the right. We have to define that direction somehow. Okay? Now, to change an object's momentum, we know that we're going to have to apply a force for some amount of time, right? We're not going to be able to just apply the force for an instant and then have the object stop. So let's take a look at the object again, okay? And we're just going to say that it has a mass m now and a velocity v. And we know we're going to have to apply a force in the opposite direction of the velocity to get this object to stop. So let's go ahead and start with Newton's second law that we often do. F net is equal to mass times acceleration. And let's remember that acceleration is defined as the change in velocity over the change in time. So we can make that substitution, and we can say that F net is equal to mass times the change in velocity over the change in time. And we can reorder that. F net delta t. Let's see if I can undo that. There we go. Is equal to m times delta v. And I can see here, look, in keeping this situation really simple, I can see here that the only force is going to be the applied force, so I can go ahead and say, in this case, F applied times delta t is going to be m. And delta v, right, anytime we have the change in anything, we know delta v is just v final minus v initial. So I get m times v final minus m times v initial. Well, since we've defined momentum as mass times velocity, that simply becomes F applied times delta t is equal to the final momentum minus the initial momentum. And finally, I can write that as F applied times delta t is equal to a change in momentum. And we can clean that up a little bit. We can put our vector hats on there so that it's all just right. This quantity right here, this applied force times time. So remember in our last unit we talked about work, and we said that work is just force times distance. We defined that. We're going to define impulse now as a force times time. So this is impulse, and we said this is change in momentum. We can use I to stand for impulse. I know your book uses J. I usually use I. I is equal to delta P. This is our impulse change in momentum equation. We can use this equation as long as the force is constant. Now, if the force isn't constant, we can't use our impulse equation, right? Because we said that impulse is the force times the change in time. But if the force isn't constant, we can't use that. We can, however, look at a graph. And there might be a mastering physics problem that looks like this. Oh, let me do that. Time. And so if our graph looked like this, right, force versus time, and force would be measured in newtons, time would be measured in seconds. The area of this graph would be the impulse. Actually very similar to looking at a force versus distance graph, and the area under that graph would be work. So for those of you in calculus, you would be able to see that I is simply the integral of f dt. So We've talked about 3 really important equations that would love to make their way into your study buddy for the final, or this sheet in the back of your notebook, or the special sheet you have in Notability. And these 3 equations are that momentum is mass times velocity, impulse is force times time. You can put delta t there as well. Let's go ahead and do that. We'll put delta t there. And that impulse is equal to momentum. Now let's take a look at these units real quick. We said that the units for momentum were kilograms times meters per second. What about impulse? What are the units for impulse going to be? Well, impulse, the units for impulse are going to be, it looks like, the units for force, which is a newton, times the units for time, which is a second. Well, that at first glance looks like they might have different units for impulse and momentum, but they can't. If impulse is equal to a change in momentum, and let me fix my equation here. Impulse is equal to a change in momentum, there we go, then those units wouldn't work out. They have to be the same unit. So let's take a look. A newton second, we know a newton is also a kilogram meter per second squared times a second. Well, this second here cancels with that squared, and a newton second really is just a kilogram meter per second. So you can use either of those units when you're talking about impulse or momentum, either newtons times seconds or kilogram meters per second. It does not matter. So similar to energy, we're going to talk about conservation of momentum as well. A little bit different. It's not exactly the same. So we're going to look at conservation of momentum. And we're going to say that momentum of a system, right? So we might have more than one object, just like when we looked at energy, we looked at systems, because you had, for instance, if you were dropping something, the earth was part of the system if you wanted to say that energy was conserved. So we're going to say that momentum of a system is often conserved. And we're going to look at 2 different examples of this. Explosions. Okay. Now, this is not like 4th of July fireworks. Okay, this is in physics for now. All we're going to look at is an explosion is going to be where 2 objects push off from each other. So hopefully you can already see the lab we're going to do. We're going to have 2 lab carts. We're going to put a spring in between them. We're going to release the spring, and the 2 objects are going to push off, and we're going to see how momentum is conserved. And then we're going to do kind of the opposite, and we're going to talk about collisions where 2 objects run into each other. Can you have more than 2 objects? Absolutely. We're going to keep it simple for now. We're going to leave it as 2 objects run into each other. Now we said that momentum is often conserved. When is it conserved? Well, if no outside force, that's why we have to be careful when we define our system, because if the system is 2 carts, then the 2 carts pushing on each other is an internal force. So we have to see if there's any outside force. So if there's no outside force providing an impulse, then we know that momentum is conserved. So why is that the case? Let's take a look at our impulse equation with momentum, change in momentum. If I is equal to delta P, that just means the force times some time is equal to P final minus P initial, right? We put our little vector hats on there. Well, if the force is 0, that means that 0 is P final minus P initial, and you can see where we're going. The final momentum has to equal the initial momentum, so that means that the quantity is conserved, right? Our initial is equal to our final, so we're going to end up with conservation of momentum. So what does that look like? That looks like here's 1 cart, and it has a mass, let's call it M1, and it has an initial velocity of V initial 1. And then we have a second cart, and let's call that mass M2, and it has an initial velocity in the other direction of V initial of cart 2. Now, public service announcement here. If you, so far in physics, have decided that you don't need to use subscripts, You don't need M1 and M2 because you can keep that all straight in your head. You should know that that method is about to crumble and crash around you. If you do not use subscripts and keep a very good track of the quantities with which you are discussing and using in your equations, you will not have very much success in this unit. You have got to use subscripts for mass, for velocity, because we're going to have all kinds of different masses here. We're going to have all kinds of different velocities here, right? This 0 just means initial of cart 1, of cart 2, right? The different masses. Otherwise, you're going to put M and then another M and then another M, and they're all going to look the same, and you're going to cancel them out of your equation, and that is not going to work for you. So please be very careful with your notation. You're going to want to use those subscripts, okay? So this is our initial condition, and they're going towards each other, so we're certainly going to have a collision, bam. And what happens after the collision? Well, we're going to have cart M1, and you can imagine that it's probably going to be going to the left now, so that's going to be its final velocity. We're going to assume it's on a frictionless surface of some kind. And then we're going to have cart M2, and it's going to be going to the right now, and we're going to call that V final of cart 2. Okay. So we see that there's no external forces. We can use this idea that the final momentum has to be equal to the initial momentum. The other thing we can look at, just like we did with energy, is we could say, well, we could phrase this as the change in momentum 1 plus the change in momentum 2 has to be equal to 0. So if one cart gains momentum, the other cart has to lose momentum. Okay? If one increases, the other one has to decrease. Okay? The way I'm going to phrase this for now is that the initial momentum of cart 1 plus the initial momentum of cart 2 has to equal the final momentum of cart 1 plus the final momentum of cart 2. And we know that momentum is just mass times velocity, so we end up with M1 V naught 1 plus M2 V naught 2 is got to be equal to M1 V final 1 plus M2 V final 2. Now, a lot of people like to try and memorize this equation. I don't suggest it simply because you can always derive it, right? Don't memorize these equations because there will be plenty of times where this equation doesn't work and you'll have to use something else. So please don't memorize this. Think about the ideas, right? Think about these initial 3 equations because this is what you're going to be given, all right? You can always look those equations up. This you don't have to memorize because you can always get there with your vast knowledge of physics, okay? Now we're going to talk about 2 different types of collisions. We're going to talk about an elastic collision, and then we're going to talk about inelastic collisions, okay? In an elastic collision, we're going to say that the total kinetic energy, right, and very specific here, the total kinetic energy before the collision is the same as the total kinetic energy after the collision. We don't say that it's conserved because during the collision, the kinetic energy is actually changing, okay? So the total kinetic energy before the collision is the same as the total kinetic energy after. So think about this perfect idea. In a perfect world, we'd take a tennis ball and we would drop it onto the floor. Well, when the tennis ball hits the floor, that's a collision. And we haven't talked really about that, right? We've talked a lot about dropping things, but our timer always stops the instant the object hits the floor, because we didn't know enough physics to worry about anything after that. So we know, hopefully, that when it hits the floor, its velocity is net zero, right? We've been talking about that a lot. But now we can figure out what happens after it hits the floor. So if it's an elastic collision, what happens is that the tennis ball hits the floor and the tennis ball deforms. And all of that kinetic energy becomes something else. Well, what does it become in an elastic collision? It becomes elastic energy. So our tennis ball, if you look at a tennis ball and you watch a video of it hitting an object, a tennis ball will compress a whole bunch. And that compression is just like a spring compressing. So the spring compresses, right? It stores all that energy. And then when the spring releases, it releases that energy into something else. So in an idea of a tennis ball, the tennis ball hits the ground. All that kinetic energy becomes elastic energy. And then as the collision comes to a stop, the elastic energy is released. It becomes kinetic energy again. And the ball goes up to the same height it was released from. Now, in reality, we know that doesn't happen. What actually happens is that the tennis ball hits the ground, some of that kinetic energy becomes elastic, and some of it becomes something else that we can't use anymore. You guessed it, it becomes heat. So a lot of the energy is stored as elastic, then it's released and becomes kinetic, and the ball goes higher, but it doesn't go as high as it was originally released from, because we know that some of that original energy, that original UG, that eventually became all KE, only part of that then became elastic, the rest of it became thermal. In a perfectly elastic collision, all of the energy would have been converted back to kinetic energy. So what we just talked about with the tennis ball is an inelastic collision. Okay? In an inelastic collision, the final kinetic energy after the collision is less than the initial kinetic energy. If we have a perfectly inelastic, then what happens is that the two objects stick together. So this time, instead of thinking about dropping a tennis ball, think about dropping a lump of clay. Right? In that instance, when I drop the lump of clay, all of the UG becomes KE, then that KE all becomes thermal energy, and the clay does not bounce. Okay? Energy is still conserved, right? We can't violate the law of conservation of energy, but all that mechanical energy has now become thermal energy. So in a perfectly inelastic collision, what you see is something like this. Here's M1, and it's got some initial velocity, and here's M2, and M2 is just sitting still, right? Its initial velocity is 0. And then bam, cart 1 runs into cart 2, and afterwards, cart M1 and cart M2 are moving along together at the same speed. So you can call this V final. Okay? All right, that's all for the notes that I have for you today. Check Schoology, see what else you should be working on. Thanks, guys.